All right, hello. Um, we're going to be talking about gravitational fields. I'm pretty sure everyone knows. Well, I'm pretty sure you know what a gravitational field is. You have two types, radial and uniform. So, if we look at the Earth as a whole, we'd see that its gravitational field looks radial, which means that all the gravitational field lines basically converge at the center of the Earth. But for for us humans on the surface of the Earth, if we zoom into this image, um, on the surface of the Earth, we see that it's flat, and that's just because the Earth is so big that for us it seems flat, and so it appears that all the gravitational field lines are just uniform and are 90 degrees to the surface. Now, gravitational field strength. So this right here is a very important definition that should be remembered. So it's basically the force experienced per unit mass by a small point mass placed in a gravitational field. So this is the formula for it, gm by r square. And we get this by equating this, which is the formula for the gravitational force, and we equate this to this formula. And we cancel out mass, and that leaves us with acceleration, which is basically g, and that's gm by r squared. So that's pretty simple so far. Okay, so this is gravitational potential energy, and it's the amount of energy that's stored between two masses, and this energy is stored within their gravitational fields. So this is a little difficult to think about or imagine. So another way of thinking about this is that the gravitational potential energy of two masses is basically the work done in bringing those masses to their present position from when they were infinitely apart. So if we look at this, these bodies were initially infinitely apart, very, very far away. And what we've done is we've used some energy in order to bring these bodies to their current position where they are right now. So that's basically gravitational potential energy. It's the amount of energy required to do that. Now, there's a very important assumption here, which is that when we're bringing these masses together, it's done at a very, very slow speed, so that kinetic energy is negligible, and it's purely potential. Okay, so we've looked at what gravitational potential energy is. Let's look at the formula. If you want to use calculus in order to figure this out, well, this is how we do it. We integrate the formula for gravitational force within the limits r, which is the distance between the two masses, to infinity. And after this, we eventually come up with this, which is our formula for gravitational potential energy. The symbol for gravitational potential energy is a little different from what you'd really expect. It's EP. And you might be wondering why there's a negative sign here. So an obvious explanation is that through the process of integration, a negative sign is created. But another way to think about it is through something called a potential well, which basically means that if this is the gravitational potential energy right now, you would need positive of that same amount of energy in order to separate the masses to an infinite distance. So let's look at a diagram to really understand it. let's say this is a potential well. So what that is basically at this point, at this level, which is very, very far away from the Earth, you would have basically zero gravitational potential energy. But on the surface of the Earth, you would have this much gravitational potential energy. Which means if you want to escape, if you want to get this rocket perhaps to climb out of this well, you would need this amount of energy. Okay, so now that we've kind of got the idea of that, let's look at an example. So the question is, find out how much energy you would need to take that rocket from the surface of the Earth to point B. Okay, so it's this rocket, and we have to figure out how much energy we need in order to take this rocket from here up to this level, or to point B. So these are some values for mass of the Earth, mass of the rocket, and basically all we have to do here is just calculate what the gravitational potential energy of the rocket is here, and then calculate what it would be over here. So by doing that, we basically get these two values, and now all we have to do is just figure out the change in this gravitational potential energy. You just have to figure out how much the gravitational potential energy changes by when going from here to here. And that's about this much. 6.8 into 10 to the power 9 joules. So in other words, that's how much energy you need to provide to this rocket to get it from the surface to point B. Now, it's important that the assumption applies here that we're moving the rocket at a very slow speed so that kinetic energy is negligible. Okay, so now we're going to go to a concept that's similar to gravitational potential energy, and that's just gravitational potential, and its symbol is Vg. So again, this is an important definition, especially for the IB physics exams. So looking at the definition, it's basically the work done per unit mass and bringing a small point mass m from infinity to point B. Okay, so we know that it's a work done per unit mass, right? So we can write gravitational potential as W by m. And we know that work done is just change in gravitational potential energy. And we know that gravitational potential energy is minus gmm by r. So we can substitute that in the place of work done. And then we get this, which simplifies into this as the mass cancels out. So now this is our new equation for gravitational potential. There's one important thing about this quantity, and that it's a scalar quantity. And we'll see why that's important later. Okay, so let's say I have a mass. Let's say I have a giant mass here, some planet. And it's going to produce a gravitational potential at some point around it in its field. Perhaps here. So if we put a mass, if we put a small mass m over here at this point, then the gravitational potential energy of the system would become m times Vg. Now, if this mass was moved to a different point, so if we took this as point A, take out m. If we took this as point A, but now we move this to point B, then the work done required to move that mass from A to B would be, well, like we saw earlier, the change in gravitational potential energy, or m mass times the change in gravitational potential given here. Right, so work done equals change in gravitational potential energy, which is the same as mass times change in gravitational potential. Okay, so here we'd be able to understand why the idea that Vg is a scalar quantity is important. So say we have two masses. This weighs A kilograms, this weighs B kilograms, and we've considered an arbitrary point P. The distance from mass A to P is x, distance from mass B to P is y. Okay, if the question is to calculate the total gravitational potential, just gravitational potential, at point P, all you would have to do is basically figure out how much gravitational potential is being created by each mass. So using this formula, let's say I want to figure out how much gravitational potential is being created by this mass. I would just do Vg is equal to minus g, it's the universal gravitational constant, times m, which in this case would be A, because that's the mass, divided by x. And then I would do the exact same thing for this mass. And if I just add it up, just plainly add it up, that would give me the total gravitational potential at this point. I think a better way to visualize it would be to just take a point here, say let's call this point C. Okay. Now if you were to calculate the gravitational potential at point Z, you would use this exact formula and just substitute the values. You'd find the distance between point Z and each of the masses, and then use this formula in the same way that we just used it now to calculate the gravitational potential at point P. So again, you'd have, if I were to take this mass this time, if I were to take mass B, then for point Z, let's assume this distance is about, say, C. Okay, so then Vg is equal to G B by C. So yeah, there's no consideration of direction, it's just the magnitude of gravitational potential from each planet, and we're adding that up to find the total gravitational potential at point C or at point P. Okay, I think that's all. I hope this video helped, and thank you for watching.